Okay, so this is joint work with my Facebook colleagues Peter and Nikos and our collaborator Ilya from Yale NUS. I'm going to start off by motivating a problem that engineers at Facebook encountered that sort of catalyzed this work that we did on race detection. So in late 2016, some Facebook engineers were working on Litho, which is this declarative UI framework for building performant scrolling UIs. And basically, the way this framework works is if you're implementing a piece of UI in Litho, you encapsulate all the logic for creating your piece of UI in a Litho component. And you write separate logic for fetching data, things like talking to the network, going and downloading the photo that your friend has posted to your Facebook newsfeed. Measuring and layout, this includes things like you download 10 comments, the layout is going to decide, oh, I'm going to show only the first 3 and collapse the rest of them. And then drawing, which is actually taking this layout and all the resources you have and actually rendering them and showing them to the user. Once you've implemented one of these components, what happens is the Litho framework will schedule these different jobs for you. So for the fetch data, that's going to be something expensive talking to the network. It'll schedule that on a background thread so it's not blocking the UI and making it unresponsive. And the measure and layout step and draw operations, because they actually involve touching the UI, will be scheduled for the UI thread. So in late 2016, what these engineers realized is that even though this measure layout step is really closely related to drawing the UI, it doesn't actually need to touch the UI thread. So if in the Litho framework they change the scheduler to schedule this job on the background thread instead, they could potentially get this big speed up by not blocking the UI thread as often and making things a lot more performant. The only problem with this is, in order to actually migrate this job from the UI thread to a background thread, you have to make sure that the code implementing this measure and layout logic is thread safe. And because that didn't need to be thread safe in the initial version of the Litho framework, that's potentially a problem. Because if you take code that always ran sequentially before, and now you start running it on a background thread, you have the potential for data races. So data race, of course, is 2 concurrent accesses to the same memory location, where at least one of them is a write. And although not all data races are bugs, data races usually aren't something that you want in your program because they lead to unexpected behavior. Because the scheduler is non-deterministic, a different access may win in different executions of the program, and you may see behavior that you didn't want, or you may see a crash, or in certain languages, you may even see undefined behavior violations of memory safety. So in the specific case of Litho, what the problem is that this measure layout step previously ran sequentially on the UI thread, so it couldn't conflict with other measure layout steps or with the draw operation. But now that it's running on background threads, it can run in parallel with other measure layout steps and also with the draw operation. So all these things are potential conflicts, and if there's a data race, then you can end up getting something like this, which is probably not what you want from a user perspective. So put yourself in the shoes of the Facebook engineers that wanted to do this migration. Adding concurrency to code that used to be sequential is really scary, particularly when you didn't write that code. So the setup here is that there were thousands of these existing components that are being used to run newsfeed. And if you're these engineers doing the migration, the problem you have to solve is, where do I have to add synchronization to these components in order to prevent data races? And it's not as simple as just looking at the top-level component classes themselves. Data races can hide in the transitive dependencies of the components as well. So maybe you look at the top level code and it looks okay, but deep down in the call chain of some library, it's doing something that's not thread safe. So this is going to be a huge manual effort for the team doing the migration, and it's also super error prone. And the second problem is, once you've actually fixed a component and added all the correct synchronization and you think it's safe now, how do you prevent that from regressing? This is in a live code system with lots of Facebook engineers hacking on the Android newsfeed app. If someone else introduces a race, how do we detect that and prevent it? Normally, the answer for this sort of thing is you write a test, but with data races, the problem is they happen non-deterministically because of the scheduler, so it's really hard to write a test that says, oh, there's a data race, and then just block some code that introduces a new data race from landing. So there's this one-time heroic effort of doing the migration, and then there's this ongoing effort of keeping everything safe forever. So these are both pretty hairy problems, but I think people in this room would have a better idea of how to solve this than most. If you have a static data race detector, then it can show you where you need to add synchronization in the existing components in order to prevent data races. And if you run it at code review time, you can also say, hey, it looks like this code change has introduced a data race, and you can block that code change until the developers actually fix the problem. So the engineers working on Litho heard about some preliminary work we were doing on concurrency analysis, and they were considering the 2 problems on the previous slide, and they started to think, hey, actually, we don't really want to go forward with this migration unless we have a static analysis to help us out with it. So of course, we decided to talk with them and figure out what exactly it is that they needed from us. And so pretty much the first question they asked is this going to be interprocedural? You can see the comment they asked, will it be recursive? I don't care so much about finding data races just in this top-level class-like story. I care more about what are sneaky things that could be going on in its dependencies, and then in the libraries that those things use, this sort of spooky action at a distance very deep down the call stack. That's the thing that they're concerned about happening. So our analysis has to be interprocedural. It has to be scalable because the Facebook app Android app is many millions of lines of code. So if you can only handle a couple 100,000 or something, that's not going to work. And it has to be incremental because to support this use case of running at code review time, even if our analysis scales to millions of lines of code, we don't want to analyze everything from scratch every time someone changes the code. We want the cost of the analysis to be proportional to the size of the change. Another thing is that we need a low annotation burden. There's some really effective type and annotation-based approaches for detecting data races. Like there's the Clang thread safety analyzer, and there's these guarded by annotations for Java. Those approaches are really great. Like anytime you can turn a static analysis problem into a types problem, I think it's a good thing to do so. But it wasn't a good fit for this particular approach because of this massive amount of pre-existing code. You know, you have thousands of these classes, and you think of the problem of where should I add annotations to this code in order to catch the bugs? That's sort of the same as figuring out where I should add synchronization. So although these approaches are good for this particular case, that wasn't going to work. And then where we differ the most from previous work in static race detection is normally the emphasis is on soundness or catching all the data race bugs. But when we talked to the engineers, they said, you know, what we're doing here is we're taking code that's sequential and we're moving it to a concurrent setting. The bugs we're really worried about are ones that have to do with missing synchronization. We don't care so much about, you know, subtle bugs with weak memory or bugs that involve protecting the wrong data with the wrong locks. All we want to know is where are there cases where I have sequential code and I need to add some synchronization. So that sort of covers the first part of the talk, the motivation for doing this, helping out with this migration and detecting regressions going forward. And in the remainder of the talk, I'm going to go a little bit deeper into the guts of how we implement analysis that meets these design requirements. And then finally, I'll go through an evaluation where we talk about comparing RacerD to existing work in static and dynamic race detection. And also, I'll tell you how this migration went and what the status of RacerD at Facebook today is. So I'm going to start off with some background on compositional analysis. I'm not going to spend too much time on this because this isn't something that's a specific contribution of this work, but it's important to sort of see the broader framework that we write our analyses in at Facebook to understand how RacerD specifically works. So in the kind of compositional analysis we do, we're trying to compute summaries for each procedure. And when we're analyzing a procedure like P3, I can look at the summaries of its callees. Like in this case, I could look at the summary for P4. But I don't know anything about the callers. I don't know that I'm going to be called by P1 and P2 eventually. And I don't know anything about the transitive caller P5 except for whatever information is encoded in the summary for P4. And I need to compute a summary for P3 that's totally independent of the calling context. I'm not going to compute a new summary when it's called from P1 or P2. I'll compute something context independent and use it everywhere. So given that strategy, what you can do is you compute a call graph, you do a topological sort, you start from the leaves of the call graph and schedule the analysis in reverse post order. And of course, if there's call cycles, you can't do a topological sort, so you can break the call cycles by iterating to a fixed point or using heuristics to decide how to deal with recursion or mutual recursion. So in this example, you could start with P6, then analyze P5, then P4 and P3, and you get the idea. You sort of go all the way up, and eventually you've analyzed everything. So this is highly scalable because in the absence of call cycles, you analyze each procedure only once, and then that's sort of the minimal amount of work you need to do. As long as whatever you're doing to analyze each procedure scales pretty well, then your analysis as a whole is going to scale pretty well. So to give you a taste of the kind of summaries RacerD is computing and how we use them to report races, I'll just show a simple example. So we have this counter. It has an mCount field. There's a get method that returns the value of the counter. There's a private set method that sets the counter to a new value. And then I have a reset method that sets the counter to 0. So the kind of summaries we're going to compute are basically these sets of syntactic accesses. So we don't have a sophisticated abstraction of the heap at all. We're using syntactic access paths to represent the kind of accesses that we're going to report races on. What kind of access was it, a read or write, and were there any locks held at the time of the access? So for get, our summary would look like, OK, we read the path this.mCount, and there were no locks held. For set, similarly, except that we wrote the path. And for reset, we'll see, oh, there's a call to set. Let me look at the summary for set and see what's in there. There's a write to mCount, but because this method is tagged with synchronized, I'm holding it locked, so the lock count associated with here will be 1. So when we have all these summaries and we need to figure out what to report, what we're going to do is we're going to sort of look at the summaries of the non-private methods and figure out which ones access the same syntactic access path. And then if there's two accesses such that one is under synchronization and the other is not, and at least one is a write, then we're going to report. So in this case, we would say get and reset might, if the client of this class calls get and reset in parallel with each other, we might have a data race because they're touching what looks like the same memory and one of them is a write. So at a high level, the kind of summaries we're computing are these sets of what we call access snapshots, a syntactic access path, along with some other information that lets us answer these two questions of can accesses touch the same memory and can accesses happen at the same time? So to those pieces of information I just discussed, there's access paths and lock count. But we found that that wasn't quite enough to get the kind of results we were looking for. We also need to track threads that we think might be happening, might be running at the same time as the current access. And also some ownership information for each access path. Do we happen to know that the memory accessed here is owned by the current thread? And our overall domain is just a Cartesian product of these sort of four subdomains. And let me go into a little bit more detail on how the concurrent thread and ownership domains work. So the problem that this concurrent threads domain is solving is we need to know what can run in parallel with, what accesses can run in parallel with other accesses. And if you do something like assuming everything can run in parallel with everything, that's going to be really noisy. We tried it, it's really noisy. And if you assume nothing can run in parallel with anything, then you're not going to report anything. And you can do all sorts of complex approaches, like trying to look at the thread spawning graph of the program and actually like compute some whole program picture of what can run in parallel. But what we do is actually something that's a lot simpler and a lot more compositional. So by default, the value associated with an access is no thread unless we see some evidence that this code is intended to be run in a concurrent context. So if you annotate a class with thread safe, hopefully you did that because you're intending to use it in a concurrent context. We're going to treat all the accesses and methods of that class as happening under any thread. And similarly, if you use a lock, there's not much of a point of using a lock in a sequential context. So whenever you do that, we're also going to treat all the accesses in the scope of that lock as happening under any thread. There's something slightly more subtle, which is any thread but main. So a lot of the thread safety patterns in Android involve reasoning about this particular piece of code can run on the main thread, but not on background threads. And so I know it's not going to race with other tasks that are also scheduled on the main thread. And there's these methods that programmers use to enforce that. So if you use one of these methods, like here we say if thread util is .main thread, I'm going to write to this.f. We'll associate the access to this.f with any thread but main, which means that I can run in parallel with background threads, but not with the main thread. Okay, so the ownership, the problem this is trying to solve is that there are some accesses that clearly can't be involved in a race. So in the simple example, I allocate a new object and assign it to local. If I write to local, clearly that memory hasn't escaped to another thread. It's owned by the current thread. This access can never be involved in a race. And if I think that it can be, I'm going to get a lot of noise by reporting false alarms between this access and other accesses after this memory actually has escaped to another thread. And so that's the simplest case, but also there's things like, oh, maybe I have some factory that allocates fresh objects, and then I'm going to write to those. I need to understand that those are safe as well. So the approach we take here is fairly simple. The domain is ownedif of this set of things, and I'll discuss what the things mean in a minute. But ownedif of empty set means I own this thing unconditionally. I can do whatever I want to it. It doesn't leak to another thread. All the writes are safe. So when we have a fresh allocation, what we'll do is we'll map the access path to ownedif of empty set. And then when we do a write, we'll say, hey, that write is safe because this is ownedif of empty set, which just means owned. And if you have something like global.g equals something, well, there's no fresh allocation there. We don't know anything about global, so we're still going to flag that. And similarly, we'll track ownership of return values, so we'll be able to handle this case too. So what this set of things inside of ownedif is actually doing is that ownership can be conditional on the ownership of the formals of a procedure. So in this example, writeF, if A is owned by the caller, then this access to A.f is going to be safe. But if A isn't owned by the caller, then it could possibly be implicated in a race. So we'll map A to ownedif of 1, which is the formal index of 1. Index 0 is this. And we'll say in the summary for writeF, this access to A.f is associated with ownership value ownedif of 1. And then when we have a local allocation, we say object O equals no obj, and then I do writeF of O, we'll be able to propagate the ownership information in the caller to the summary of the callee and figure out that this access is safe. Finally, you have these more complex patterns like Java builders, where in setx here, if this is owned by the caller, then the access to this.f is safe and the return value of setx is safe. But if this is not owned by the caller, then it's not going to be safe. And in order to prevent reporting false alarms, when you use these sort of builder things, you have to understand both of those, and we use the same approach there. We say, if this is owned in the caller, that gets associated with the access of this.x, and then the return ownership is also conditional. So we've basically covered all the different components of the abstract domain. The way we actually use these in reporting is I'll have in hand 2 access snapshots, and I'll want to know, can these accesses potentially race? So to figure that out, all we do is we go back to our definition of data races. A data race is 2 concurrent accesses. So we say, if one of the accesses isn't under a lock, and if one of them runs in a background thread, to the same memory location, if they're the same syntactic access path, and if neither of them is owned, and where at least one is a write if the kind of one of these 2 things is writes. So basically, we'll have procedure summaries, and we'll have these sets of accesses. We have a way to aggregate and sort of check all pairs without actually paying for the cost of checking all pairs. And when all these conditions are true, we report a race. So I've glossed over many details of how the analysis actually works, in particular applying summaries. It's not particularly complicated, but in the interest of time, I have to skip it. The details are in the paper, and I'm happy to discuss offline also. So that covers the first 2 bits. Now let's look at evaluating RacerD against existing approaches and RacerD at Facebook. So we had this hypothesis in seeing how RacerD worked at Facebook, where it's filling this niche between sound static and sound dynamic analysis tools. So if this is our set of true data races in a program. A sound for a dynamic analysis means everything that it reports is a true race, whereas sound for a static analysis means it reports all true races, but may also report some false positives. And what we're trying to capture is somewhere in between, where we're going to report more true data races than a sound dynamic analysis and fewer false positives than a sound static analysis. So to evaluate this, we picked a static tool and a dynamic tool, like the best open source ones we could find, and ran against them on their home turf. So we chose Chord, which is a fairly old but pioneering work in Java static analysis, and we ran it on the decouple benchmarks that they used in this recent PLDI paper. We found that we've reported 3 times fewer alarms on all of the benchmarks, and on half the benchmarks we reported an order of magnitude fewer alarms. They did the hard work of triaging their results and finding true bugs in their paper, and we were able to find all of those true bugs plus a few more. Even though you can write a sound static analyzer, of course, like you can have bugs in your analyzer that makes you miss true bugs. So that's why that happened. And in terms of time, RacerD took from half a second to 25 seconds, and Chord was on the order of a minute to an hour and 47 minutes. So it's not just that we were doing way more work. For Droid Racer, the story is similar. Droid Racer is this dynamic analysis tool for Android. We took the triaging results from their PLDI 14 paper, and we were able to find more true bugs than they found on each benchmark. And they're also not quite a sound dynamic tool, so in 2 cases, we actually reported fewer false positives as well. The time story, similar, sort of 12 seconds to 3 minutes for RacerD, versus they didn't report precise timings for Droid Racer, but it was a few seconds to a few hours, so performance is a little better. The background layout migration was a success. Switching to the Facebook side, 2 engineers were able to migrate hundreds of these components safely. They fixed over 1,000 races that RacerD found. And maybe most strikingly is that even though we weren't going for full soundness, there were only 3 false negatives, like races that slipped by RacerD during the migration, and they weren't due to our design decisions that weren't sound. They were due to analyzer bugs that we fixed after the fact. So engineers were very happy with how this went. Most flatteringly, they said that it wouldn't have been tenable to do this migration without RacerD or Infer, which is what RacerD is built on. Going forward, the migration was a one-time thing, but RacerD still runs in production at Facebook today. Over the first year of its deployment, it reported to 500 different programmers 7,000 times, and then there have been over 4,000 races fixed. So I don't want you to leave today thinking that we solved the problem of static race detection. We certainly haven't. There are lots and lots of limitations of RacerD. So in particular, if there are races on aliased access paths that are syntactically distinct, we're going to miss them. We tried to mitigate that, but it didn't work. Similarly, we don't do any sort of escape analysis. This ownership thing is very conservative. If you have local objects that escape, we'll still think they're owned, and we won't report them. We're not fully under approximate. We tried a slightly different domain setup where it was, but then we lost too many reports. And also, this only works for the simplest of of locks. We don't do read-write locks. We don't do fine-grained concurrency. We don't do weak memory, any of that harder stuff. But the thing that's surprising is that in spite of these limitations, RacerD turns out to be a pretty useful tool for helping programmers write safe concurrent code. And although these limitations sort of sound arbitrary and based on some collection of heuristics that we chose, actually we have an upcoming, or my co-authors have an upcoming POPL paper where they formalize the assumptions that we're making and are able to prove that RacerD reports no false positives under those assumptions. So finally, RacerD, it's a scalable high signal low annotation static race detection tool. It's in production at Facebook. It's open source, and I believe groups at Uber and Amazon are also looking into using it. And going forward, we're working on getting implementation for Objective-C working, and Nikos is working on some other nifty concurrency analyses for detecting even harder problems like deadlocks and starvation.
Okay, let's thank Sam. Do we have questions?
Hi, thank you. It was great. I was wondering if you can tell what's the time it takes to run this tool in CI on the Facebook app or apps?
Yeah, good question. I can, and I have a slide for that somewhere. This one. Yeah, so let me explain what this means. This is a probability density plot of the running time in CI. So basically, you can think of all the area under the graph as the distribution of running time. So the median time you can see is about 11 minutes. And then mean is a little bit higher, 22.5. And there's a long tail of very slow times. When people do giant code mods that change tens of thousands or hundreds of thousands of lines of code, it's slow. But in a typical case, it's pretty fast.
Hi, nice work. The only cure to a data race you support is adding a lock, which means that people's code will have slowed down because they can't do anything more interesting. Do you have a record of the slowdowns?
Yes, that's a very good point. If you just lock every single read and write in your entire program, that would also solve this problem. That's certainly something that people were concerned about when we were doing this migration. Because we're being under approximate and trying to report a subset of the actual problems, we're hoping that we don't encounter this, but we don't actually have we can't actually guarantee you that we're not slowing things down. And it would be interesting to look at approaches that would show us for sure.
And so you either don't know or can't say?
Don't know.
Sorry, one more question. So this is built on top of an affair. So I was wondering if you can comment on which part of the overhead in the sense of running the analysis is due to the additional stuff that you added on top to support RacerD, and which of them are part of sort of the core infer framework, if that even makes sense.
Yeah, no, it does make sense, and that's a good question. We find that basically this interprocedural propagation, like the part I showed at the beginning, that's the really expensive part. Applying the individual functions for computing summaries is super cheap. So if I took RacerD and added an equivalently expensive analysis, there's basically no cost. Almost all the cost is in doing the sort of parsing, building CI work, and then in the upfront like construction of the call graph and doing the propagation. But the actual like analysis of a single function is very fast and doesn't really add any overhead.
Okay, that's thanks, Sam, again.